In the last classes we were discussing about power amplifiers, and the power amplifiers are those amplifiers which handle large amount of current, voltage and power. So, the transistors which are used in these power amplifiers must also have the ratings which should be higher than those which are used in small signal amplifiers. So, today we will be discussing about the power transistors which are used in power amplifiers. They are special transistors which have the capability to handle large amount of current, voltage and also can dissipate large amount of power. So, the limitations on a transistor, as we know, are from current, that is the maximum current, which is maximum rated current, and in power transistors the maximum rated current is in the order of amperes. So, it is high current, which is the rated current is a high current which is in the order of amperes. Similarly, the maximum rated voltage in a power transistor is also high, it is in the order of volts. Also, the rated power for a power transistor, the maximum rated power is in the order of watts. So, all these quantities like ampere, voltage and watts, these are high quantities, and power transistors are designed or made with higher ratings. And power transistors also have large area, that is they are made keeping in mind that they have to dissipate large amount of power. So, the area of these power transistors are also high, so that the temperature of the junction of the transistor should not be abnormally high, it should be able to dissipate the power and the temperature rise should not be high. That is why the area is also made larger. One thing to be noted is that the maximum rated current and maximum rated voltage, they cannot occur at the same time. If the transistor has a high rated current, then at that time the voltage which will be appearing across collector to emitter, that will be small, and the product of this current and voltage, that should be within the rated power, which is the rating which is written for a particular power transistor being in use. Now, if we compare a small signal power, a small signal BJT and a power BJT, as per these different parameters of voltage, current, power ratings, etc., we can very clearly see the difference between these two types of transistors. For example, we are taking a small signal BJT with the type name 2N2222A. This is one type of BJT which is used for small signal amplification, and a power BJT, its type is 2N3055. Another power BJT we are also taking, which has a type name of 2N6078, and compare the ratings as per the voltage, current as well as power, and also compare the value of the current amplification factor beta. As is shown in this table, if we consider a small signal BJT, the maximum VCE is 40 volt, whereas in a power BJT in 3055 the maximum voltage is 60 volt, whereas in the other type 6078 it is even higher, it can handle up to a voltage of 250 volt. And the current rating, if we consider maximum current, maximum collector current in the transistor, in the small signal BJT it is only 0.8 ampere that can be handled by this small signal BJT, but in power BJT this current is quite high, that we can see here, it is around 15 ampere current, that is the maximum rated current for this power BJT 3055, and in the other case of course it is a smaller value 7 ampere. And the power rating, maximum power dissipation in the BJT, if we consider at ambient temperature, which is generally taken as 25 degrees centigrade, that is taken as the ambient temperature, and the ratings are generally specified at this temperature, which is the ambient temperature. So, at that temperature the maximum power dissipation for a small signal BJT is 1.2 watt only, whereas a power BJT can dissipate up to maximum of 115 watts, as well as the other powered BJT can dissipate up to 45 watts. But the current amplification factor beta value is typically low value in power BJTs, whereas in small signal BJTs it is high, around 35 to 100 maybe the value of beta in a small signal BJT, but in power BJT that value is between 5 and 20 for 3055 and between 12 and 70 for 6078 power BJT. So, the beta value is only lower in power BJTs, but it is meant for amplification of power. So, the current amplification may be less, but overall power amplification will be high. So, the maximum rated current, that is IC rated, is basically related to the collector current at which the current gain falls below a minimum specified value. That means the specification of the maximum collector current IC rated for a power transistor can depend, it will be depending on the value of the collector current at which the current gain falls below a minimum specified value. That is, beyond that minimum specified value the current gain should not fall, because beta value is typically low in power transistors. So, beta value should not fall below a specified value, or specified beta is given beyond which below which it should not fall, and for that beta whatever the collector current value is, that is determining the maximum rated current or the current that leads to the maximum power dissipation when the transistor is in saturation. That also is a factor to determine the maximum rated current in a power transistor. When the collector current reaches the saturation value, what is the power dissipation? So, that value of the collector current when the maximum power dissipation occurs, that will be determining the rated current, maximum rated current. So, power BJT current rating, maximum rating is either dependent on the minimum value of beta below which it should not fall, or the maximum power dissipation at saturation of the collector current. So, either of these two may determine the maximum rated current. Now, the maximum rated voltage of VCE for a power transistor is related to the avalanche breakdown in the reverse biasing condition, because we know that when you go on increasing the magnitude of the voltage in the reverse biasing condition in a transistor, it will be leading to an avalanche breakdown when the current rises very sharply, but that will be detrimental to the transistor, and we should not operate the transistor in the avalanche breakdown normally. So, that is the rating, how far you can go on increasing the voltage, and that is determined by the reverse biasing condition avalanche breakdown voltage. Because if we operated beyond that voltage, the transistor should will be having the danger of getting damaged, because a very high current flows in the avalanche breakdown, and it is like short circuiting the collector and emitter. It's very enormously high current flows, and it may even lead to melting of the connecting wires, because its temperature will be very high. So, it should not be up to or beyond that avalanche breakdown voltage, which is the determining factor for the maximum rated voltage. Basically, what happens is, when you consider the reverse breakdown condition, if we revisit the characteristic curve for a transistor IC versus VCE say, and what will happen is that the characteristic are like this. When you consider the collector to emitter output characteristic, then even if you go on collector to emitter voltage, which is reverse biasing the collector emitter, because this diode is reverse bias in the collector to emitter junction. So, when you go on increasing initially, even if you increase the VCE, the collector current will not rise much, but when you go on increasing till avalanche breakdown occurs, that means an avalanche of electrons will come out from their covalent bonds, and they will be knocking out, due to the kinetic energy, they will be knocking out more and more electrons from the neighboring covalent bonds. So, it will be leading to a very high current, and that is the avalanche breakdown, and at that point actually the collector current will be rising to a very high value, and the collector to emitter voltage VCE is almost same for all the characteristic curves. That means, the characteristic curves will crowd around this VCE maximum, or this is also called VCE sustain. That means, this much of voltage is required for sustaining that breakdown, because all the collector current characteristic curves for different base currents, we are showing these characteristic curves, nearing breakdown they all will be crowding around the same value of VCE, that is called the VCE sustain. So, that voltage is the maximum voltage or rated maximum for a power BJT. So, one another rating is also important, which is coming from a fact known as second breakdown. This avalanche breakdown, which we have discussed, is the limiting value of the voltage on the power BJT that will be determined by the avalanche breakdown voltage. But another breakdown also occurs in a power BJT, which is known as a second breakdown. Now, if there are slight non-uniformities in the current density, then what happens that there will be local regions of increased heating in the power BJT, because due to this non-uniformity in the current density in the power transistor, local regions will be heated up, because this high current density, wherever these current densities are higher, they in those local regions there will be heating up. So, as the heating of the transistor takes place, so the semiconductor material will have a decreasing resistance, because heating of semiconductor means more and more carriers will be released and the resistance of the semiconductor will decrease. So, decrease of the resistance means again more current will flow. So, increase of the current will take place, and increase of the current will mean again more heating or temperature increase. Again increase of temperature will be meaning the heating will be meaning that again current will be increased, because the temperature increase means the reverse saturation current also will increase. So, current will increase again increase of current will be increasing the temperature again. So, this process is like a chain process, or it will be continuing, and so what will be finally happening is that finally another breakdown may occur due to this chain effect or cumulative effect of current increase, again increment of temperature, that again is leading to increase of current, that will be continuing and continuing until a condition will arise that the current is so high that it may melt the wires connecting the transistor. So, it will be like short circuiting the collector and emitter. So, what will be happening is that this is another breakdown due to the local non-uniform current density, and we have now another limiting condition being offered or being given by this second breakdown. So, the voltage which is the maximum voltage that it can be operated under, that is one is given by this avalanche breakdown, that is the breakdown voltage, and also another voltage or second breakdown that will be also putting a limit on the power transistor. Now, if we consider the power, maximum rated power, then we have to find out the instantaneous power dissipation in a BJT. What is the power dissipated in a BJT? Where the power is dissipated, basically that we will have to see. So, one is in the collector, that is VCE into IC, that will be the power wasted in the transistor's collector. But another also power another power is also dissipated in the base, and due to base current the power dissipated in the base region is what? VBE into IB. So, these instantaneous power dissipations taking place in the two portions of the transistor, one is the collector and the other is the base region. But generally practically IB is very smaller as compared to the collector current. So, this part of the power dissipation, that is the dissipated power in the base, is very small as compared to the dissipated power in the collector. So, we can, for all practical purposes, we can ignore or neglect the power dissipated in the base. So, this part can be neglected. So, we have the power dissipated in a transistor given by VCE IC for all practical purposes. This is the instantaneous power dissipated in the transistor. So, the maximum rated power, if we denote by PT, so that will be given by VCE into IC. Now, what will be that rating? of the maximum power dissipated in a transistor, it should be that power where in which the temperature of the device remains below a maximum value, because this is very important, because the transistor should not be heated up enormously because of this power dissipation. So, there is a limiting condition that the transistor temperature should not go beyond this value. So, that temperature is generally denoted, and so the power dissipation, maximum power dissipation is actually related to the transistor's temperature. It should not go beyond a particular temperature which is specified. Now, the transistor's operating region which is safe, that means the transistor's safe operating area has to be now considered. In which area in the output characteristic curve, if we consider which area is safe for operation of a transistor, we will be finding basically an area which is safe for operation for the power transistor, which will be limited by the maximum collector current, maximum VCE as well as maximum power dissipation. So, this area or region where the transistor can be operated safely is called safe operating area or SOA, and it is bounded by the three quantities of maximum collector current, maximum collector to emitter voltage, or that is sustaining voltage, and maximum power dissipation, as well transistor's second breakdown characteristic curve. That also we have to keep in mind, because there is a second breakdown which may happen, and we will have to take care into considering that characteristic of the second breakdown also. So, we will be having an area or a region bounded by all these 4 parameters within which we should operate the power transistor. So, let us look into that area. So, here we are showing the safe operating area. This plot is having the maximum collector current given by IC max. This is just an example having these values, it is not always that this is having only these values, but then we are considering a typical case for an example. And the VC is sustaining voltage, that is here is given by this upper bound on this collector to emitter voltage, and the power dissipation in the transistor is given by this curve, because we know that power dissipation in a transistor is basically the collector current IC into the VCE, that is collector to emitter voltage. So, when the VCE will be smaller, then collector current will be higher, that is very obvious from the output characteristic of the transistor. When VC is very high, IC will be less. So, basically it will be a hyperbola given by this dissipation power dissipation in the transistor, and this curve will be specifying that maximum value of the power that can be dissipated in the transistor. So, the region below this is the safe operating region. So, at any point, any operating point, you can find out what is the power dissipated in the transistor. Suppose at this point, what will be the power? It is given by this voltage into this current. So, in this way, the maximum power at each point, I mean if we connect, or if we draw this curve connecting all these points, we get this curve for the maximum power dissipation, which is a hyperbola. And also there is a second breakdown region given by this curve. So the second breakdown also puts a limit on the operating area of the transistor. So at no point of time we should go outside this safe operating area for the BJT, or even if we go out, we should not stay there for long. That is at some time we may go outside this safe operating area, or we may operate the transistor outside this area, but it should not be operated for long. And for safety, we should be within this safe operating area. Now we have seen that the transistor which is used in power amplifier, as it handles high power, so what happens is that it increases the internal temperature or the junction temperature of the device, and it should not be above the ambient temperature, which is specified as 25 degree centigrade. So as this power dissipation is invariably associated with temperature increase or the transistor device being heated up, so there must be some schemes for reducing the heat. That is why heat sinks are used. So heat sinks are used with the power transistors to take care of this heating caused due to the high power dissipation. So these are special packagings for power transistors, which will be incorporating a heat sink, and this heat sink will be just bolted into the transistor, which is again inside a case. So the transistor which is used, the device, will be packaged first with a case, and that case will be bolted into the heat sink. Now the operation or the use of this heat sink is that it will conduct the heat from the junction of the transistor into the surrounding air. It will be dissipating the heat, or it will be conducting the heat to the surrounding air, and so that the junction transistor remains cool. So the example of heat sinks and the casings which are used for transistors is shown here. There are different varieties of cases which are used in transistor, and here these casings are of different shapes also, and the transistor will be inside the casings, and apart from this casings, the heat sink will be there, where there is a hole where it will be bolting the transistor case. So this is a one example of a heat sink, and the packaging for the power transistor, if we look into, it is a sink on which the cases of the transistor are bolted, and there are fans also inside the heat sink. Actually the fans will be there for cooling the transistor in the heat sink. So it is just a picture for showing the heat sink along with the transistor case. So basically what are there? One transistor which is the device, it will be first put into a case, and that case will be again bolted into the heat sink. So the flow of the heat is first from the junction device to the case. Now the case to the sink, and then finally the sink to the air. And we can now visualize this as a flow taking place from the junction of the transistor into the finally the surrounding air via this medium of case and then heat sink. So, what is happening is basically we are visualizing the flow of the heat which is analogous to electrical voltage and current. If we consider the transistor power which is dissipated as say P, which is nothing but the thermal power in the element which is a transistor, then across this element the temperature difference which is occurring, let us take it as T2 minus T1, which is equal to P into theta. Theta is the thermal resistance which is given in degree centigrade per watt. So, basically this is analogous to an electrical law, like in the left side T2 minus T1, the temperature difference, if we consider that as voltage, the difference in potential, and in the right side this power flow can be considered as the current flow, which is multiplied by this resistance theta. Theta is the thermal resistance. So, current into resistance is voltage or potential difference. So, using that analogy, we will be now visualizing the power flow in that way, where the difference in temperature across the element that is occurring because of this power flow through this resistance. So, here a circuit representation of this power flow or temperature change across an element or a device is shown here. So, the electrical analogous circuit is shown here, where the theta is the thermal resistance. So, we are now considering a transistor, but that transistor is not naked, it is having first put into a case. So, how the power flow is happening? First of all, the transistor device to case, that is the first flow between the transistor junction and the case, and then from case to the sink, heat sink, and from heat sink to the ambient temperature. So, these are the stages. So, if we consider the transistor device at this end and the air at this ambient air at this other end, so this is the transistor device and the other end is the ambient air. In between we have this resistance offered by the case, that means the resistance from device to case, and then from the case to the heat sink, and then from sink to the heat sink to the ambient temperature. So, these three resistances are there, and theta 1, theta 2, theta 3. So, theta 1 being theta device to case, theta 2 is case to sink, and theta 3 is sink to ambient. So, the total temperature difference from the device to the ambient air is T device minus T ambient air, which is nothing but T device minus T case, that means device to case of the transistor, plus T case to T sink, that means the case to the heat sink, and then finally heat sink to the ambient temperature, ambient air. And at these two ends, this is the current which is actually analogous to the power dissipation. That means power is like having a flow from the transistor to the ambient air. So that is why it is shown by arrow, just to have the analogy with the current flow. And what is this power flow producing? It is the temperature difference. So the as the current flow causes the potential difference between these 2 points having these resistances, similarly the power flow from the transistor to the ambient air is causing the difference in the temperature from the device to the ambient air. So this analogy is used to understand the power flow from the transistor to the ambient air. So what will be now the temperature difference between the device and the final ambient temperature? That difference is T device minus T ambient is equal to PD, that is like a current, multiplied by this whole resistance, that is theta device to case plus theta case to sink plus theta sink to ambient. So that is written here. It is like same current is flowing, producing the voltage across these three resistances by multiplying it by the resistances. This is when a heat sink is used. If a heat sink is not used, then of course there will be the power flow from the device to the case and the case to the ambient air, because in between stage, that is from case to the heat sink, will not be there. This is not applicable when heat sink is not used. So we will be having simply the difference in temperature between device and the ambient equal to PD, power dissipation, into theta device minus case, theta device to case, that is the thermal resistance from device or the transistor to the case, plus theta case to ambient. And typically the ambient value, ambient temperature is taken as 25 degrees centigrade, and the transistor rating, maximum power rating of a transistor is also specified as at ambient temperature 25 degrees centigrade. That means if we are having a transistor rated power as PD at ambient, we mean that at ambient temperature 25 degrees centigrade, this is the rated power of the transistor. So if now we consider the maximum device temperature or maximum junction temperature of the transistor as Tj max, then we can simply write down what will be the PD max for the transistor, Tj max minus T case by theta device to case, because here the maximum device temperature PD max is meant. So as here we have seen, that is PD max, and that will be denoting the maximum power dissipated in the transistor, and also if it is specified that you have this Tj max as the maximum device temperature. So this difference between Tj max and T case divided by theta device to case, that is the PD max. We are concerned about the transistor and the case. Now there is a curve which is known as power derating curve, which is a plot between the PD max and T case. That is, if the temperature of the case is varying, the maximum power dissipated also will be changed, and this point where T ambient is 25 degrees centigrade, that means the case temperature is 25 degree centigrade, then the PD rated is defined at that temperature. That means the PD rated or the rated power of a transistor conforms to, or it specifies to, the ambient temperature 25 degrees centigrade, which should be the temperature of the case. So, if it is beyond that, if we allow for the case temperature being higher than 25 degrees centigrade, then obviously the rated power will also decrease. So, similarly, we just have a look here up to maximum temperature of the case. If the Tj max it reaches, then the power dissipation is 0. That means we cannot allow any power dissipation at when it is the temperature is Tj max. So, this power derating gives the idea about how the maximum power dissipated is related to the temperature of the case of the device or the case of the transistor. So, we will have to take into care all these factors of maximum current rating, maximum voltage rating and maximum power dissipation of the transistor when operating it for power amplifiers, and we should always operate the transistor within the safe operating area. Now, let us try one example relating to this power transistor. Determine the required current the voltage, required voltage and power ratings of a power BJT used in the circuit shown in figure below. We are given a power transistor with a circuit as shown in figure. It is a common emitter transistor and VCC being applied is 24 volt, and this resistance, which is the collector resistance or load resistance RL, is 8 ohm, it is given, and a signal is applied Vi. This point is emitter, this point is base, this point is collector, and we have to find out basically the ratings of this transistor. It is a power amp, it is used as an amplifier using a power transistor. This is the output voltage. So, in order to know the maximum collector current and maximum collector to emitter voltage, we have to draw the load line, or we have to write the equation of load line. That we can do if we consider a DC condition. The collector current flowing is IC in this direction. So, writing the equation for this output circuit, VCC minus IC into RL minus VCE is equal to 0. That equation is the governing equation. So, that we will be writing VCC minus IC into RC minus VCE equal to 0 using KVL in this output circuit. Putting the values, VCC is equal to given as 24 volt minus IC into, this is RL, it is written as RL in the circuit. Actually this is the resistance in the collector and it is written as load resistance because the voltage is obtained across this RL and RL is given as 8 ohm minus Vc equal to 0. Now, in order to know the load line, draw the load line, what we require is the maximum or extreme points of the collector current as extreme point of the collector to emitter voltage. These 2 points we require to draw the load line. So, in order to know the maximum collector to emitter voltage, we make IC is equal to 0. Put IC is equal to 0. Putting IC is equal to 0, what we get? That VCE max, that is equal to 24 volt. So, one point is known, this is 24 volt, and putting VCE is equal to 0 to know the maximum collector current, we put VCE is equal to 0. So, putting VCE is equal to 0, what we get? Maximum collector current IC max, that is found out as 24 by 8 means 3 ampere. This point is 3 ampere. So, you notice here we are getting 3 ampere, not milliampere. It is a power transistor. This is 24 volt. So, joining these 2 points, we get the load line, DC load line. So, now these two are the limiting voltage and current ratings for the power transistor. Now, what about the maximum power rating of the transistor? So, to know the maximum power rating of the transistor, we must consider this power being dissipated and find out the maximum condition. So, what is the transistor power? Transistor power dissipated that is equal to say PT and VCE IC, that is the power dissipated. So, what is this VC? We can write down VCC minus IC RL into IC, and that can be written as VCC IC minus IC square RL. So, this power, in order to be maximum, we are to find out the maximum condition. So, maximum power can be found out when IC is maximum, that is, in this expression if we look into, the variable is IC. So, we are to find out the condition of maximum collector current for which the maximum power will be dissipated. So, the current at which maximum power will be dissipated is given by what? You find out the maximum condition from this equation. PT is equal to VCC IC minus IC square RL. So, we have to differentiate PT with respect to IC and put it equal to 0 to get the maximum condition of the collector current. So, using that, the PT differentiate the power with respect to collector current, make it 0. That means, we have to differentiate this expression VCC IC minus IC square RL, make it equal to 0. So, when we differentiate it with respect to IC, it will be VCC minus twice IC into RL, that is equal to 0. Or what is that maximum collector current? we get VCC by 2 RL, and VCC is equal to 24 volt, RL is equal to 8 ohm. So, we get 1.5 ampere is that current for which the power dissipation will be maximum, and this is the current IC at which PD will be maximum. And what is the corresponding VCE for that maximum power? So, the corresponding VCE for PD max equal to, simply putting that equation again, VCC minus IC RL is equal to VCE, 24 minus IC we have found out to be 1.5 into 8. So, that is 24 minus 12, that means 12 volt. So, we got a point for maximum power dissipation as 12 volt 1.5 ampere for PD max. So, plotting this in on the load line, if we look into the load line again, draw the load line again, IC, VCE, 3 ampere maximum collector current, 24 volt the maximum VCE, drawing this, joining these two we get the load line. So, having the slope of 1 by RL with a minus sign. And now, this is the maximum collector current, which is the maximum rated current for the power transistor 3 ampere, maximum rated voltage for the power transistor 24 volt, and we are now having this point PD max at around the middle of the load line, because we are having that point as 12 volt and 1.5, exactly at the middle of this load line we get the PD max. So, multiplying these two we can get the PD max. What will the PD max? Maximum power dissipation equal to 12 into 1.5, 18 watts. So, 18 watts is the maximum power dissipation for this transistor. So, here we are getting all the ratings of this power transistor. The ratings are IC max is 3 ampere, VCE max is 24 volt and PD max is 18 watts. So, this is the safe operating area bounded by this. The power dissipation will be like this. This is within this will be the safe operating area below this curve and bounded by these two lines. And for this transistor we are getting PD maxes at this point and corresponding voltage and current at this. Now, if we have lesser power dissipation, suppose it is somewhere away from this value, here or here it can be, this is the point where the maximum power dissipation is occurring for that particular power transistor. And for different resistance value, of course, RL if it is changed, we will be having different power dissipation. So, your point of maximum power dissipation will vary and corresponding voltage and current will also vary. So, we will be having that hyperbola within which we should remain. The product of this current and voltage should give you a value below this power hyperbola, that is the safe operating region. And similarly, if we consider a BJT, with rated power of 20 watts and a maximum junction temperature of Tj max equal to 175 degrees centigrade. The transistor is mounted on a heat sink with parameters theta case to sink thermal resistance is given as 1 degree centigrade per watt and theta sink to ambient is 5 degree centigrade per watt. Now, you have to determine the maximum safe power dissipation in the transistor. So, this deals with the problem of power dissipation with a sink. So, how to find out the safe power dissipation? We know the power dissipation which is rated, PT rated, that is given by Tj max minus T ambient. T ambient is 25 degrees centigrade, even if it is not mentioned you should know it, divided by theta devised to case. So, PD rated is given as 20 watts and that is equal to Tj max is given as 175, T ambient is 25, theta devised to case is given as that is not given, we have to find out theta devised to case. So, from this we get theta device, thermal resistance between the device and the case is equal to 175 minus 12 by 20. So, that is 7.5 degrees centigrade per watt. You are asked to find out the maximum safe power dissipation, PD max, that will be equal to Tj max minus T ambient. Now, heat sink is there. So, the sink to ambient thermal resistance is given. So, we will be having Tj max minus T ambient divided by theta devised to case plus theta case to sink plus theta sink to ambient. That quantity of the division between this Tj max minus Tm and this whole thermal resistance will give you the safe power dissipation, and that maximum safe power dissipation can be found out by putting these values of Tj max 175 minus T ambient 25 and all these thermal resistances. If we put, that is given theta devised to case we have found out 7.5, case to sink theta is 1 and sink to ambient theta is 5. So, this value if you calculate we will get 11.11 watt. So, this is the maximum safe power dissipation in the transistor, 11.11 watts. Although the maximum rated power is given as 20 watts. So, although rated power is 20 watt, the safe power limitation is less than rated power, as is seen here. 11.11 watts is the safe power dissipation, which is found using the sink parameters. Although the rated power, that is from device to case, if we consider only from device to case, the rated power dissipation is given as 20 watts, but along with the sink and device to case, we will be getting the safe power dissipation as 11.11 watts. So, this example shows how the sink effectively introduces safety in the transistor's power dissipation capability. So, in today's class we have seen about the parameters of power transistor. Power transistor which is used in power amplifiers have specifications given by maximum current, maximum voltage, maximum power dissipation ratings as well as second breakdown. And we should operate the power transistor well within the safe operating area given by all these upper bounds, and we have also seen the use of heat sink to conduct the heat generated in the transistor while dealing with such large magnitude of power, and seen how effectively heat sink dissipates the power or conducts it into the surrounding air, keeping the temperature of the power transistor within limits.